of graphs. So I'm going to remind you of a couple things. And one of the things they asked for in the homework, can you go over to the left-hand side? And Kayla, will you just kind of explain what we talked about with on the far left graph? You're muted right now, so I need you to unmute. And I'm going to make sure that you're presenting here. So here we go. All right, you're up. You're live.
So this is when you add a strong base to a weak acid.
Yep.
Yeah. Strong base to a weak acid, and there's a portion here where before it gets to the equivalence point where it's the prime buffering time. So that's what we call the buffering region. And the halfway point in the buffering region, which is the half equivalence point, is the best buffering point.
Yep. And if you notice here, when we're buffering, see how the line evens out completely? Can you write pH on the left-hand margin? Because in all of our graphs, pH is in the margin, and down below is the amount of the strong that we're adding. In this case, we're adding strong base. Now, if you take a look here at the graph up above to the right-hand side, so that looks an awful lot like a weak base being titrated with a strong acid. And incidentally, so you know this, all titrations, all of them, will always be titrated with a strong. So what's being dropped in, what's doing the titrating is always going to be either a strong acid or a strong base. Another way of saying that is that whatever is being dropped in is always going to be either H plus or OH minus. Strong, just pure OH minus, pure H plus. Now, if you notice here, if we were going backwards, you see how there's also a buffering region on that little graph as you go down, kind of between, yeah, right in that region right there. So if we had a half equivalence point, the half equivalence point would be in the center of our buffering region. And then what's kind of cool about this is that however much OH, in this case here, you're adding H plus. Can you say H plus added on the bottom? And put like an arrow going towards the right so everyone knows that we're adding H plus when we're going towards the right. Wow, you just totally froze there, and all of a sudden you're on your y-axis. And the y-axis is pH. Okay, good. If you put a dot down below on that's kind of equivalent to the half equivalence point right on the x-axis. Kayla? You're freezing on me. Okay, you're completely frozen. Can you guys still hear me? Okay, I think you just came back. Okay. Okay, now you're frozen again. That's unfortunate. What's odd is that you're frozen and I can still see everyone else. Can you maybe ask the sub to perhaps just walk down the hallway to the tech room and see if someone can help us out?
You want one of us to go to the tech room?
No, I was asking if maybe the sub could go to the tech room, but you're back live right now. So let's take advantage while you're still moving. Okay. All right, so come back to the graph here. And so let's take advantage of the time while it looks like it's okay. So if you drew a line on right below on the half equivalence dot on the baseline, so just draw a line right there. So whatever the distance is from 0 to the half equivalence point, that's the exact distance between the half equivalence point and the equivalence point in terms of the amount of H plus you add. I need everyone, like, that is an incredibly pivotal piece of information because we know, if we know the number of moles it took us to get to the half equivalence point, we know how many moles it took us to get to the full equivalence point, because the half equivalence point always requires exactly half the amount of big dog dropped in as the equivalence point, and vice versa. If I told you it takes 4 millimoles to get to the equivalence point, then you know that it took 2 millimoles to get to the half equivalence point. Can I get a thumbs up if that makes sense to you here? And that's where understanding how graphs work really help us. The other thing you need to be aware of is this. If you go back to the weak acid, weak base graph that you got on the left-hand side. So put your finger on the equivalence point, please. We call that the equivalence point or the stoichiometric point, yeah? Now, that point, since we were titrating a weak acid, that point will be above 7, because when you titrate a weak acid, Can you write an equation underneath there? Can you just write OH, or can you write um, OH minus plus HA? Okay, so that Ha represents every single weak acid in existence, yeah? And when it forms, it is going to form, it's a one-way street, hon. The big dog equation is always a one-way street. Okay, it's going to form A minus plus H2O. Now, really quickly, if I have, let's say I have 4 millimoles of HA, right, and 4 millimoles of A minus.
Which one is it?
We're starting off, yeah, right. So watch. If I'm titrating right there, at the end, I'm going to have 0 of my OH minus, 0 of my HA, and I'm going to have 4 millimoles of my A minus. Now, see if this makes sense to you, if your reasoning senses work on this. If all I have is a weak acid, can you put your finger on the HA?
Wait, what?
You put your finger on the HA? Okay, at the beginning, all I have is 4 millimoles of HA. At the end, I have 0 moles of HA, and I have 4 millimoles of the A minus. That's the only thing that's left in the solution is A minus. So what do? We take that A minus and we throw it into water. So can you write the equilibrium expression for that, please? Now, what I need you to be aware of here is this. Can you circle the A minus on the bottom there? No, right there. Circle that. Okay. The reason, and that's we're talking about, this is what's happening at the equivalence point. The equivalence point is when we've used up exactly how much of the acid we start off with. So see how we have 0 of the HA exactly? There's no leftover OH minus, because if there was leftover OH minus, then we just jump to that to figure out the pH. But whenever we get to the equivalence point, the conjugate is the only thing that's left. So see if this makes sense to you here. You don't even have to do the work on this, but just think this through. If all I have is a weak acid and I completely use it up, at the equivalence point, all I'm going to have is a weak base. If I have a weak base and I throw it into water, won't it produce OH minuses? And those OH minuses, won't that make the pH above 7? So what you need to be aware of here is that whenever we're titrating a weak acid, we're always going to end up with a pH above 7 at our equivalence point. Why? Because at the equivalence point, all we have is the A minus. In fact, let's do a little naming here. Can you put at the 0 mark? Can you just write HA? Just write HA. So would you agree with me? At the 0 point, we haven't added in any of the big dog. We have only HA. Now go to the half equivalence point. Don't we have both HA and A minus? So put HA and then a slash and then A minus, right? And then as we move up to the equivalence point, what's the only thing we have at the equivalence point? Don't we have only A minus at the equivalence point? And in between Ha, can you look at the 0 point, please? Put your finger on the 0 point. Between Ha and the half equivalence point, you start getting less and less HA and more A minus until at the half equivalence point, you have exactly the same amount of HA and A minus. If you keep on going up the curve, can you run your finger up the curve from the HA? Yeah, right there. As you keep on moving up, now we get more and more A minus and less HA until we reach the equivalence point. And at the equivalence point, we have absolutely no HA and only A minus. So if you're asking, and one of the things they like doing is they'll say and they'll give you 2 different points on the graph. And they'll say at the equivalence point, what are the major species you have? Major species are just kind of asking what are the ions that you have in solution. And so at the equivalence point, all you'd have is A minus. And if all you have is A minus at the equivalence point, then that's a base by itself, and that will produce OH minuses. Now, let's flip to the reverse graph. Okay. So now in this case here, aren't we adding HA to A minus? So can you write the big dog equation, please, underneath? I'm sorry. The big dog equation is A minus plus H plus. Do you understand that that's because we're titrating a weak base in this case, right? So at the very top, and our starting point, all we have is A minus. At the half equivalence point, when we have A minus and HA, and at the equivalence point, when we have Ha, not H plus, HA. And at the half equivalence point, I don't know if you put Ha or H plus, but it should be HA. Because at the half equivalence point, don't we have the same amount of acid and conjugate base? In this case, if you can you do me a favor on the actual big dog equation, can you underline A minus and HA? That's your acid and conjugate base pair, right? Now, I don't know how you guys found this when you're doing weak base titrations. I think we do 80% of the time, 90% of the time, the one on the right. The one on the right, we're titrating a weak base. We're titrating A minus or any weak base, right? We tend to not do very many weak base graphs, and so we get a little bit confused when we see them for the first time. But they're exactly the opposite of their weak acid counterparts. Any questions for me on these two graphs? Anyone? Okay, so I'm gonna put a pin in this here. This is the points on the graph. I'm gonna keep on coming back to graphing because, as I said, AP board is in love with graphs, so we're going to revisit this. But I want to do this. I want to go all the way back to chapter 14, and I want you guys to turn to page 682, or for those of you who are looking here online, I want you to do interactive example 14.15. Your hair is delightful, Autumn. Okay. Zion, what are you doing? Well, not both. Now Jackson's in Zion's screen. Oh, gosh. All right. I guess I kind of asked for that. So what I want to do right now is I want to talk about polyprotic acids and weak acid mixtures. Okay. Now, one of the things that, and you can erase everything. Yeah. So go ahead. And can you write on the board, calculate the pH of a 5.0 molar H3PO4 solution?
I was still reading.
Okay. Calculate the pH of a 5.0 molar H3PO4 solution. H3PO4 solution. And then the equilibrium concentrations of H3PO4, H2PO4 minus, HPO42 minus, and PO43 minus. Essentially what we're doing is just pulling a hydrogen off each time. H2PO4 minus, HPO42 minus, and PO43 minus. We want the equilibrium concentrations of those. Okay, so let's acknowledge here that the H3PO4 has 3 hydrogens that can be pulled off, the H3PO4. And so once we pull the first hydrogen off, we're going to end up with an amphoteric solution. You're going to end up with H2PO4 minus that can be with an acid or a base. So one of the things that you need to be aware of is this, and let's just write this down on the side or let me emphasize it. Whenever you're figuring out the pH of a polyprotic acid, you use only the H pluses from the first dissociation. So whenever you're figuring out the pH of a polyprotic acid, use only the H pluses from the Ka1. Now let's do this together. And by the way, just so you have the Ka values here, let's actually write all the dissociation equations and leave a little space in between each one. So let's start off with H3PO4, Actually, let's not leave any space. This is right, all of them right on the side here. You guys should probably write them on your paper as well, just so we can work off of them. Plus H2O, it's going to go to H2PO4 minus.
Right here.
Yes, please. H2PO4 minus plus H3O plus. Okay, and then take the H2PO4 minus. Fill it with water, and tell me what you come up with, and then do the same thing for the okay. Can you write next to the first equation, can you write Ka1 and then Ka2 next to the second one, and then Ka3 next to the third one? And let me give you the values for each of those Kas. So Ka1 is 7.5 times 10 to the negative third. Ka2 is 6.2 times 10 to the negative 8. And Ka3 is 4.8 times 10 to the negative 13. We might have to switch over to a black pen because it's starting to fade here. It's a little bit hard to see on the screen. Okay. Okay, so let's look through this real quick. Would you acknowledge if you compare the Kas, the Ka values are times 10 to the negative 3, times 10 to the negative 8, and times 10 to the negative 13. Now, if you understand that Ka, isn't that essentially a ratio between our reactants and our products over our reactants? Can I get a thumbs up if that makes sense to you? Our Kas are always our products over our reactants. So in each case, doesn't it make sense that if you look at the Ka1, it's times 10 to the negative 3, and the Ka2 is times 10 to the negative 8. That means that the amount of product that's being produced in the second K is on an order of 10 to the 5th smaller than for the first K. Just so you have an idea, this is approximate. For those of you who are mathophiles, it's not exact. But you're talking about 100,000 times less being produced in the second step than the first step. And then you compare your first step to the last step. Isn't that times 10 to the negative 3 versus times 10 to the negative 13? Okay, so that's a times 10 to the 10th disorder. Now that's, if I'm doing the math right, I think that's 10 billion times less. So if I'm trying to figure out the pH for a solution, can you circle the very first H3O plus up there? No, I'm sorry. H3O plus, not the H3PO4. That. Okay. That's the H plus. And I again, a gentle reminder that H3O plus and H plus are the same thing. Yeah. Thumbs up on that. Just as it's a general reminder. Yeah. So my H3O plus, I'm going to try and figure out that amount of H3O plus, and because just put an arrow to the H3O pluses in the second and the third step. Okay, if you compare the amount of H3O plus in the first step compared to the second step, and even compared to the third step, the amount of H3O plus or H plus in the first step is going to be so amazingly big compared to the H plus in the second step that it'd be like adding a billion plus 1 or a million plus 1. That plus 1 is not going to be an impactful value. So I come back to my original statement. Whenever you're figuring out the pH for a polyprotic acid, you use the H plus from the first dissociative step, and that's it. So let's go over to the right-hand side and let's do a nice problem, please. We're doing Ka1 here. Oh, that's fantastic. H3PO4. You might have to tilt the camera over a little bit to the right. And by that, I mean, yeah, perfect. Okay, so they started us off in this problem. They started us off with 5 molar. So an incredible amount. Let's do an I initial. Let's do ICE, and my initial amount of H3PO4 is going to be 5 molar, which is again an obscenely high amount there. Let's ice it. And can you write me the do me a favor, write the law of mass action with the actual variables in it first, like you normally do, and then let's plug the variables in.
I even write I all the time. It's not like I. Can we not do the factor several because it's into the -3?
That's a really good point. It's going to be, you can, because look, take a look at the concentration we're starting off with, 5 molar.
That's a lot.
That's a huge number, right? But we can verify it. Let's try it. And if it doesn't, if it's not 5%, then we'll have to actually plug the numbers in.
Well, when I do that.
Just for practice doing this, I'd really encourage all you guys to do it. Giving nap time. Giving nap time. Okay, did you get it, Kayla? Can you tilt the screen down a little bit because it's not picking up the very bottom?
0.72.
Okay, so this is kind of a big deal. I want you to, that H plus concentration, the 0.190. That's going to be our concentration. And let's be really clear here. Isn't the H plus equal to X, but isn't also the H, can you, the screen up, you have to adjust it a little bit higher because I can't see the.
Okay, well, you asked me to look.
I know, but then you went a little bit too low. And what we may have to do is we may have to squish everything in, like you have to write a little bit closer to the top each time. Because that way we'll get the whole screen in.
I love that face.
Okay, now I can't see the bottom, of course. Okay, so watch. Since the X is equal to 0.190, that 0.190, can you put your finger on the X on next to the E? Okay, that's equal to the, yeah, right there, those two X's. That X right there is 0.190, and so is the H2PO4 concentration. So when we start the next step, the concentration we're starting with the H2PO4 minus is not 5 molar. We're actually starting it with 0.190. So we're going to do the next step here. So why don't we go over and let's shift the screen over this way to the right more. You can, but how much room do you have to the right?
There's only so much space for the laptop to go.
Yeah. Okay. All right. So let's now do the second dissociation, and let's try and write as high up as you can on the board, because we're going to run into the same problem, and we're going to write kind of smaller if we can as well. So the second dissociation is H2PO4 minus. Okay, so I should have stopped you before you started. Here's the problem. Pause. Kayla, you got to stop. So watch. Initially, didn't we have 0.190 molar, right, of the H2PO4 minus? But then we also have 0.19 molar of the H3O plus. So in our second step, we're not starting with 0 H3O plus. We're actually starting with 0.190. Sorry, I should have caught that. Does everyone see this here? Now, in this case, we should be able to do the 5%. Will anyone verify in the first step whether or not it was less than 5%? I forgot to make comment on that. You're going to see something really cool here at this for the second dissociation. What do you notice here? 5% rule there, and how about 5% rule for the x for the if 0.190 minus x is 5% rule, wouldn't 0.190 plus x be 5% rule? So what does that give us? What does that make x equal to then?
The K.
X is equal to Ka. Let's remove the h plus h. That's not equal to h plus. Kayla, x is no longer equal to h plus. See where you wrote x is equal to 6.2? That is not equal to h plus. That's actually equal to my HPO42 minus. Can you put that next to it? So let me tell you what we've done. And can you, and I know this is a pain for you, can you slide the laptop back to the original equations?
Love is a strong word.
Okay, so what they're asking you to do in the problem, oh, that's dizzy making. Okay, what they're asking you to do for the problem is they're asking you to solve for the pH. The pH can be figured out from the first Ka, which we did. We figured out the x. We figured out that x is equal to H3O plus, and then we took the negative log of that, and we got that the pH of H3PO4 is 0.72. But the next problem they're asking you to do is they're actually asking you to solve for the concentrations of all the other ions that are involved as you dissociate one hydrogen after another. So in our second step, they're asking us, what is our H2PO4 minus concentration? Are you with me right now? The H2PO4 minus concentration, isn't that also in? So do me a favor, can you put your finger on the X on the first equation? So isn't the X equal to H3O plus and also H2PO4 minus? So they asked us in the original problem, can you go back to the original, put the blue on the original? They asked you to figure out the H2PO4 minus, right? So right now, originally, can you go back to can you point to the blue you're fine where you are. Point to the blue up above. H2PO4 minus. Put your finger on that. Okay, after the first step, we can figure out both the H3PO4 and the H2PO4 minus. How? Because don't we know what the X value is? That's going to be equal to H2PO4 minus. But they also asked us for the H3PO4 minus, or H3PO4. How can we figure out the H3PO4? Wouldn't that be 5 minus whatever our X value was? So what we want, as we go through this problem, I want you to kind of do a growing tally of all the concentrations that we already know. After the first step, we should know the H3PO4 concentration, the H2PO4 minus concentration, and the H3O plus concentration. Which means that in the second step, we should be able to figure out what the HPO4 2 minus is.
Where? Someone do that. No, not at all. Oh, yeah. Are you looking for the concentration of H3PO4?
I have a question.
Yep.
Okay, so you said by the first equation we should know H2PO4 minus.
Yep.
But in the next equation, we use H2PO4 minus again, and we subtract X.
Correct. And how big is X compared to the H2PO4?
Oh, okay.
It's going to be less than 5%.
But the first time for H3PO4, that X wasn't less than 5%, so that didn't matter?
It wasn't less than 5%?
I mean, was it? I just you told us that we had to do 5 minus X. It wasn't just 5.
Okay. Kayla, can you mute yourself for a second, Kayla?
What?
Can you mute yourself just for a second? We're fine. We're fine. Don't mute. So Jackson can probably hear me still. So watch. His question was this. So put your finger on the H3PO4 where it says 5 minus X. Okay. So what he was asking, he's like, okay, didn't we have to subtract X from the 5? And I said, yes, but that amount should give you very, very close to what 5 was. What was the actual number? 4 point, what is it? 4.81. So I'm assuming that if we took was it 0.192 and divided it by 5, we're going to be less than 5%. Can anyone verify? Because if it's not, then we actually can't do the 5% rule and scratch out like we did. We're going to actually have to do.
Can we, if we're already so far into the problem, can we just assume that 5%? Like
yes, yes, absolutely, absolutely. But now because your calculators are so advanced, you can actually do it without that and still be okay. Okay, so watch. Can we slide back over now to the last equation you were doing? The H2PO4 minus equation. Okay, so now watch. We know what our initial amount of H2PO4 minus is. Can you put your finger on that? 0.190. Now, the reality is, aren't we going to lose a little bit X amount of that? But in reality, when we get done, if they're asking what is the equilibrium concentration of H2PO4 minus, even if you subtract X, we want to be awfully close to 0.190. So we're okay with just saying 0.190 is the equilibrium concentration of H2PO4. That's what we got in the first step. But the HPO4 2 minus, can you put your finger on that, please? That is solving for X, and that's what we need. Now, understand something here. Put your finger on the H3O plus, the 0.190, okay, plus X. Okay, put your finger on the 0.190. X is so small compared to the 0.190 that the reality is that 0.190 is what we're going to use in every single H plus concentration throughout the rest of the problem. So if you take a look at this right here, our H at the very bottom, isn't our X equal to 6.2 times 10 to the negative 8? Now, again, you realize how small that number is, right? Times 10 to the negative 8. So if I were to subtract 0.190 by 6.2 times 10 to the negative 8, that's an incredibly tiny number, an incredibly tiny difference, right? What do you end up with, Kayla? Does anyone have the number?
It's small. It's still 0.19.
Where does the actual decimal come in? Do you have it? Where does it go?
8, 9.
Can you write that whole thing out just so we can get a visual? So it's 0.1. You say 8, 9 repeating.
9, 9, 9, 9, 9, 3, 8.
How many nines? Sounds like the.
Okay, so take a look at that. If we're seeing whether or not 0.190, when we subtract X from it, whether it's still pretty close to 0.190, I guess that 0.189999938 is pretty darn close. In fact, let's do this. Let's do the percent dissociation in this step just for fun. Can someone take the 6.2 times 10 to the negative 8 and divide it by 0.190? I just want to see what is the percentage that actually leaves, just so we can verify that the amount of X that's being produced for the H3O plus is so minimal. I don't want only Jackson doing this. If you guys can all punch in your calculators, that'd be great.
Is 3.26 times 10 to the negative 5%.
That's after, is that after you punched in times 100?
Yeah.
So we're talking about 3.25 times 10 to the negative 5. So that's 0.0000326%. That's how much left. So are we safe? Can you put your finger up on the H3O plus where it says 0.190 plus X? Are we safe in saying that if we add 0.1899939 to 0.190, that essentially we have 0.190? Is everyone okay with that? That's why for our H plus concentration, we use what we got in the first step for the rest of the problem. So right now, does everyone have any questions on this? You can erase the percent dissociation because they're never going to ask that for the second step. But I just wanted to do proof of concept to let you know how incredibly small the amount that's associating actually is. So right now we have the H2PO4 minus concentration. We have the HPO4 2 minus concentration. What's left is our last equation. So let's do the last equation. And remember, our starting point right now, won't it be the X value that we had originally? Or the X value that we got in the last step for the HPO4 minus. And then won't our H3O plus starting point still be the 0.190? Okay, can you camera down a little bit, please? So they can see the ice. Wonderful. So let's do ICE.
I did it too big. Well,
What happened there?
I did it too big.
Thank you.
He's stealing. Oh, he's stealing.
You shut up.
No. He's stealing.
Why all of a sudden can I not see Jackson and Zion? That bothers me greatly. Jackson's in the back of the room, but I don't even see Zion on my screen anymore.
You noticed I was gone.
Even if you're not
Mr. Demetrius, my laptop's about to die.
I'm so
Just FYI, I got an email from Tech saying stop going to ask them for power cords. You have your own. That's directly from them. So obviously you're going to be using your laptops through the entirety of my class. So make sure you have them charged. Okay, Kayla. Real quick here. Will all you guys agree that if the X was negligible compared to the H plus concentration in step 2, won't it be ridiculously negligible in step 3? And when you solve it all the way out, I'm going to have to.
Wait, that's why I was confused. Because if it keeps getting more negligible, then in the end, won't the pH be super similar to like the start?
Yeah.
So then, like, why are we doing?
That's the whole point. That's the whole point. What we're saying is that the pH after 3 dissociations is going to be almost identical to pH after 1. So in order to figure out the pH, we don't have to do these 3 steps. But they didn't ask you to figure out the pH after these 3 steps because we know it's going to be almost identical. You're absolutely right. The X is the H3O plus in all 3 steps is going to be incredibly close to 0.190. The reason that we're actually doing these 3 steps is because they asked us in the problem, oh, by the way, tell us the concentrations at equilibrium of HPO4 2 minus, H2PO4 minus, and PO4 3 minus. That's the only reason we're doing these. Because if not, you're absolutely right. There's no reason. Like, notice how we're not solving for pH in any of these steps? Because the whole point is that you can solve for pH with the first step alone. Great question, though. Does that make sense?
Yeah.
Okay. Let me draw a correlation here, because this is a sidebar here. Do you realize that if you have a combination of acids, so let's say you have a mixture of acids. Are you all with me? Whenever you have a mixture of acids, you can always get the overall pH by solving an ice problem for the acid that has the greatest Ka. Let me give you an example.
Race.
Yes. Can I get someone to remind me to come back to strength, structure, the role of structure on the strength of acids, and also acid and base salts, because those are 2 things that I've skipped over so far, but I want to come back to that with you. How much time do you have left in class? Only 5? Oh, poop. All right, so I'm gonna come back to that. But let's say I had 2 weak acids, and someone help me out with Ka values. If I had like HCN and HF, can Jackson, can you look up the Ka for HCN?
Jackson. You want to look up the Ka for HCN.
Look up the Ka for HCN.
I don't know.
Can you on the board write HCN Ka equals, and then can you write HF Ka equals? Oh wow, nice.
Brayden! What was the other one? Is this like a mixture of acids?
Yeah, I just want to do a mixture of acids problem real quick. Did we not? Do you not have the Ka table, Jackson? Do I need to look it up? Okay, I'll find it here real quick. So if you look under your in the AP Chemistry,
So literally,
chapter 13 notes, worksheets.
Okay, I got it. What does he need?
HCN.
HCN is 6.2 times 10 to the negative.
And HF.
HF is 7.2 times 10 to the negative 4.
I don't think I heard you. 7.3.
So let's say I said I give you 0.3 molar of each one. What is the pH? Make sure there's a decimal in front of that 3. It looks like it's just 3. Okay, watch. This is a typical problem. They give you 2 acids. They're going to give you 0.3 molar of each, and they're going to ask you, hey, what is the overall pH for this mixture? And if you had to include both of them, you realize that they both have a common ion of H plus, and they both would mess with both your equilibriums. But here's the truth: whenever you have a mixture of acids, you can figure out the pH from solely figuring out the H plus concentration from the stronger of the 2 acids. Put your finger on the HF's Ka, please. 7.2 times 10 to the negative 4. Look how much bigger the Ka is for HF versus HCN. Ridiculously bigger, right? On the order of 10 to the 6th bigger. So just like we did with the H3PO4 with the polyprotic acid, if we wanted to solve this, all we'd have to do is solve for the H plus concentration from HF, and that H plus concentration will be the dominant H plus concentration for the entire problem. So you won't even have to figure out anything for the HCN. Incredibly important that you understand this, especially if you see a problem like this.
Oh, because of the Ka.
The Ka is way, way bigger than the other one. Now, if you ever have 2 Kas and they're really close to each other, then you're up the creek, because then there's just no way you can figure out what the pH overall is. Well, I've really shrunk the number of people that are on their computers right now. Make sure you have chargers next time.
.01 high. No.
Now, just so you're knowing this here, the H plus concentration, you go with me here? The H plus concentration we got there is 0.0150 molar. if I were to compare that H plus concentration, let's say I'd done the same exact ice problem for HCN, the H plus concentration from that would be so minimal compared to the H plus concentration from the HF that it really is a non-contributor to our overall pH. That's why we can do this with only one acid. All right, I had wanted to get into pH titration graphs, but we aren't going to have enough time. So I asked you guys to print out 3 worksheets, right? Let me just jump to it. I'm going to share my screen with you right now so you can see what I'm doing.
Maybe. Do you have them?
Okay.
Yes, it's gels.
Okay, so your homework tonight is going to be the pH, titration, and buffer worksheet. Yep, that's right, all 3. And the next class period, we're going to focus on, it's really important you have these graphs. We're going to focus on the polyprotic acid graphs and how to solve them. Nope. You didn't do the pH, titration, and buffer worksheet one because I don't believe we had done titrations yet. You did one that was called pH and H plus, but
He makes it all.
I think we have done
Yeah, I think you have that.
this one. This one.
let me see. You did that one with titrations?
Yeah.
How did you solve with titration?
Hello?
How did you start? How did you solve the problems with titration then?
I don't know. We did it. I just know that we did it. I remember. Do you remember Karina and I were asking
homework
about this
10.
last one?
Oh, that's right.
Where it was like the ratio.
That's homework 10, bro.
Yeah, I hear you. That's really odd. Okay, I'll give you your assignment. It'll probably be minimal. I'll put it on the portal.
They're alive.
Okay.
See you guys later. Thank you, Kayla.